and welcome to another WJEC A-Level Physics question. This one is question 4 from January 2014's PH2 paper, and it's a refraction question. For the first part of the question, we've got light approaching a medium of refractive index N2 from a medium of greater refractive index N1. We're going to add to the diagram to show what's meant by the critical angle. So I've partially drawn the diagram already. I've labelled the incident ray, the normal, and the refracted ray. At the critical angle, the refracted ray will pass directly along the boundary between mediums 1 and medium 2, or if you like, the refracted angle will be 90 degrees. In this case, the angle between the incident ray and the normal is our critical angle C. Next, we've got to show in clear steps that sine C is N2 over N1. So what we're going to do here is we're going to apply Snell's law, which is N1 sine theta 1, or in this case theta 1 is C, is equal to N2 sine theta 2. And theta 2 here is 90. Sine of 90 is 1. So we have that N1 sine C is equal to N2. And then clearly sine of C is N2 over N1. For the next part of the question, the diagram shows light travelling into the core of a multimode fibre at the greatest angle to the axis so that no light can escape into the cladding. So in other words, this angle here is the critical angle C. We're told, making use of the equation from A2 and marking angle C on the diagram, which we've already done, show clearly that S is equal to N1 over N2 times X. Well, in this triangle we have an angle, an opposite and a hypotenuse. So we can say that sine of C is X over S. And we also know that sine of C is N2 over N1. That's what we derived in the first part of the question. Let's do a little bit of an intermediate step and just cross multiply so that we get X times N1 is S times N2. And then clearly we can see that S will be N1 over N2 times X as required. Next we have to calculate the time taken for a pulse of light to travel 1.2 kilometers through the core in a straight line path parallel to the axis, given that the refractive index of the core is 1.5. So the first thing that we have to do here is actually work out the speed of light travelling through the core. So we can do that by taking the speed of light in a vacuum, 3 times 10 to the 8 meters per second, and dividing it by the refractive index of the glass that is travelling through. And that will give us 2 times 10 to the 8 meters per second. Finally, we can simply use time is distance over speed to find this time. So the distance is 1.2 kilometers, 1.2 times 10 to the 3 meters, over 2 times 10 to the 8 meters per second. So if we do that on a calculator or whatever, you will find that we get an answer of 6 times 10 to the minus 6 seconds, or 6 microseconds. Next, we're asked to calculate the extra time taken for the pulse to travel through the 1.2 kilometers of the core via the zigzag path shown in the diagram. We're going to use the equation that we just derived. So what we can do here, I'll do it a long way and then I'll mention a quicker way that we can do it. We can actually calculate the length of this zigzag path by taking 1.5 for N1, 1.485 for N2, times the 1.2 kilometers that we had for the length of this fibre. And that will give us 1.212 recurring kilometers there. We can find the time for this path in exactly the same way. So we're going to do 1.212 times 10 to the 3 divided by the same speed, 2 times 10 to the 8 meters per second, because remember that the light is travelling through the core, and that will give us 6.06 microseconds. And then the difference in time, the extra time, is the 6.06 microseconds that we've just worked out. Take away the 6 microseconds for the original path, and that will give us an answer of 0.06 microseconds. Now next we've got to calculate an upper limit to the number of pulses per second that can be sent through 1.2 kilometers of the fibre without overlap occurring. And we've got to state one assumption that we're going to make. The assumption we're going to make is that the pulses have negligible length themselves. In other words, the time it takes to send the pulse is very, very tiny. The last answer basically gives us the amount of time that we've got to leave between pulses to guarantee that pulses will arrive at the other end of the fibre in exactly the right order. If we send pulses too quickly, then it's possible that a pulse taking the quickest path will arrive before a pulse taking a longer path, even though they may have been sent in a different order there. So what we must do here to find the number of pulses per second is we're just going to take, let me just write this down 1 second, number of pulses per second. We're just going to take 1 second and divide it by the 0.0606 microseconds that we just worked out. So if we put that into a calculator, we end up with 16.5 million. Obviously you can get error carried forward here for any rounding that you've done earlier on in the question. Thank you very much for listening. Please remember to like and subscribe and feel free to add any comments. Goodbye.